Exactly. As we were saying. So the stress is unknown. The stress in the steel rod is unknown. So it is still what we are looking for. And at the end of the day, we have to denote it. We have to denote it by the symbol as usual. Okay. And the area, we said that this dot means multiplication. The area of our steel was 490.9375. Okay. So let's put it over here. 490.9375. Exactly. Okay. So I can close this bracket and then now put this one aside it like this, as simple as that. Plus um the stress of copper. We don't know, but you realize that we know the um, area of copper, and the area of copper was 765. Okay, that is 765. 765.8625. Okay, 0.8625. Okay. Let me quickly close the bracket. As simple as ABC, as simple as you are seeing over here. Okay. So what are we supposed to do next? We know that the load is equal to 120 kilonewton, which is the PT. It was given to us in the question. We even wrote it in our given. Look at it over here. You see the load. This is the load over here, as we wrote initially. Okay. So let's quickly put it over here, and that is 120 kilonewton. We say that 120 times 10 exponent 3. Okay, so 120 times 10 exponent 3. Okay, times 10 exponent 3. As simple as you are seeing over. So whatever thing we are written over here, we have now. So at the end of the day, we just have to make one of this the subject, and then we can find for the other. But because two variables are unknown here, we have to make this equation 2. Then later we can discover equation 3 from the compatibility condition to solve the problem simultaneously. Okay. So finally, this is going to give us a product of this. You say always you should write the numbers before the variables. Okay. So this is actually going to give us 490. This is now going to give us what? 490. Okay. Whatever you are seeing over there, after the multiplication, is going to give us 490. Okay. 490.93. 490.9375. 490.9375. Okay. Then I can bring my hot stress. Okay. So this is it over here. This is multiplying it. Okay. Plus this 2 is going to become hot 765. Okay. 765.8625. Okay, that is 8625. Okay, multiplying hot stress hot C. Multiplying stress C. So as you are seeing, all is going to now be equal to what? 120. 120 times 10 exponent 3. 120 times 10 exponent 3. You see, exactly. Exactly. So at the end of the day, we can denote this as our equation 2. We don't have much space, but we can still find a way to fix it there. Okay. So just as we did for this was our equation 1. This is now going to be our equation 2. Okay. So this is now going to be our equation 2. Okay. So this is now our equation 2. Okay. This is now our equation 2. And this is our equation 1. We can really denote it well for you to see so that understanding during learning can be easier. So this is now our equation 1, as we have been saying earlier. It's the same song we have been singing. This is still the same equation 1 over here. Don't get confused. So now this is our equation 2. Okay, this is our equation 2. Now we are done talking about the equilibrium condition. We want to talk about the compatibility condition. Okay. So we want to talk about the compatibility condition. We say that we are solving the problem, but we say that it will always be expressed in a form of what? Equilibrium condition and compatibility condition. So once you are done with the equilibrium condition, you have to come to the compatibility condition. So this is my compatibility condition. This is my compatibility condition. Compactability condition. Okay. So this is the compatibility condition. So this is the compatibility condition. Okay. What did we learn previously? We learned and we said a lot of things that for the compatibility condition, the change in length in material 1 will be equal to the change in length of material 2. So in this case, so the change in length in the steel rod will be equal to what? The change in length in the hot copper tube. Okay. So the change in length in the hot copper tube. Exactly. 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 So we are saying that but we know that the L, the change in length, it can also be expressed in so many ways. Okay. But the change in length can also be expressed in so many ways. Okay. That is, but change in length itself. Okay. We know that but change in length itself is equal to what? Let's say stress over elasticity. Okay. But change in length itself equals the stress of elasticity times what? L. And someone is asking why. That is because this is from the idea that change in length is equal to what? Strain, okay, times what? Length, okay. And this is what, if you continue to deduce or if you continue to simplify, you are going to get what I'm going to write over here. Okay. So that is finally, your relation is going to become this. Let me put it in this curve bracket over here. And at the end of the day, I'll only have to denote it with what. So finally, we are saying that our change in length, okay, is going to be equal to what? Stress, okay, over elasticity. Okay. Stress over elasticity times the length. You see, stress over elasticity times the length. Okay. As simple as ABC. As simple as ABC. As simple as ABC. It's because we know that what? The strain is equal to what? Stress over elasticity. From the idea that if we know that, let me just put a small box over here. If you know that elasticity is equal to stress over what? Strain, then it means that to get strain can also be written as what? Stress over what? E. Okay. From cross multiplication and making one the subject. And that is the idea that brought about this equation you are seeing over here. Don't get confused. On this note, I continue to say that the laws of physics are the same for all observers in a uniform motion relative to one another. On this note, I continue to say that the laws of physics are the same for all observers in a uniform motion relative to one another. Because the materials are made of the same length. Because the materials are made of the same length, this L is going to be omitted. Okay. So I'm saying that also, comma, our length of steel. Okay. That is also, we are saying that our overall length, okay, our length is equal to what? The length of the steel is equal to what? The length of the hot copper. Okay, so from that relation, it implies that the formula we are going to adopt to solve our problem will be this. That is the stress over hot. From whatever you have seen over here, we are just going to adopt stress over elasticity. Okay, so let me denote this as this, and that is written as finally our change in length. The formula we are going to use is what? Let's say stress over hot elasticity. Okay, stress over elasticity. Stress over elasticity is because the lengths are the same. They will cancel out. They will cancel out. So at the end of the day, look at what is going to happen over here. Finally, we can substitute whatever we are saying in our hot compatibility condition, and we can denote this as our equation 3. We can denote this as equation 3. So in our equation 3, we realize that our change in length of the steel rod is equal to the change in length of the copper tube. Okay. So from that same idea, we can be able to express this in terms of that. Let me quickly rewrite that again for you to see something. And that is, we are saying that the change in length of the steel is equal to the change in length of the hot copper. Okay. Let me put this over here. Okay, so this was the equation 3 I'm talking about, which I just wrote earlier somewhere. And if I want to express this, the one I have taken in terms of that, then it means that I can write that, or that is going to give us, let's say, the change in length. Okay, that is going to give us something like this: stress of the steel over hot elasticity of the hot steel. Okay, uh, which is equal to, let's say, the stress. Okay, the stress of copper over the elasticity of copper. Over the elasticity of copper. Okay, so finally we can rewrite this in good terms, and we are good to go. Okay, I'm only saying this because we know the values. We know, let me say, we know um uh, elasticity of steel rod. We also know the elasticity of the copper. Okay, so we can substitute that into the relation to make life much more easier or beneficial. So let's proceed, and that is going to give us something like this. So this is the stress in the steel rod over the elasticity of steel was 2 times 10 exponent 5. That is 2 times 10 exponent 5. Okay. Is equal to the stress of the copper. Okay. All over 1.2. Okay. Times 10 exponent 5. So at the end of the day, if we do cross multiplication from this, you realize that we can get a relation. We are going to get a relation. So let's quickly do the cross multiplication. This guy will multiply this guy, and this one will also will multiply this guy. So finally, that is going to give us, let's say, our stress of steel rod or the stress in the steel rod times 1.2 times 10 exponent 5. Okay, now we can bring our equal to sign. And also the stress in the copper is also going to be multiply, let's say 2 times 10 exponent what? 5. You see what is happening over here? 2 times 10 exponent 5. And finally, this is going to be our equation 4. So finally, this is going to be our equation 4. So finally, this is going to be our equation 4. And don't get confused at all. If there was space, I would have written it linearly. Because there is no space, that is why I'm just trying to represent it diagonally. So this is our equation 4. Okay. So from the same equation 4, if we can just make one the subject and find for the other. Okay. So from equation 4, at the end of the day, we have 4 equations. Okay. From wherever we started to where we have gotten now. Okay. From wherever we started to where we have gotten now, we have 4 equations. We have been able to establish 4 equations. Yes, this is where we have gotten to, how we have come so far. So let's continue from where we are. Let's continue from where we are. So now we want to calculate for stress in the steel rod. Okay, we want to calculate for stress in the steel rod. So we can just rewrite that as a subtopic and calculate for it. If I want to do that straightforward, many or majority may get confused. Okay, so now let's just quickly write a small subtopic and then or let me just write this over here. So right now we want to calculate for what? Let's calculate for this one first. Okay, let's calculate for stress in the steel rod. Okay. So in calculation of the stress for steel rod, I'm going to rewrite whatever we are having at the top over here. Then I can divide. Okay. And so this is the equation we are having. So that the stress in the steel rod times times 1.25, okay, times 10 exponent 5 is equal to the stress of the copper, okay, times 2 times 10 exponent 5. So from here, what do we have to do? We just have to divide. Okay, we have to divide. For teaching purposes, I'm going to repeat this one last more time again before I divide so that the steps can be clearly defined. The steps can be clearly defined. All right. Francisca wanted to ask a question. Please, you can kindly unmute yourself and then ask your question.
Sir, please, the first side, the stress of the steel rod is 1.2 times 10 raised to the power 5. But you've done it 1.25.
Okay. Thank you very much. Okay, I'm very much grateful.
You're welcome.
Exactly. Exactly. So from here, we have to just divide. Okay, we have to divide. So let's divide. And we divide because we are looking for the stress in the steel rod. Okay, so we divide here by 1.25. 1.2. Okay, so this is 1.2 times 10 exponent 5. Okay, we also come and divide here by 1.2 times 10 exponent 5. Okay, so let me use a different color pen to cancel out, and this will take care of this. Okay, so finally, what are we left with? Well, finally, we are left with the stress in steel rod is going to be equal to the stress of the copper rod uh, times what? 2, okay, times 10 exponent 5, okay, and that is going to give it all over 1.2 times 10 exponent 5, okay. So now this is going to give us, let's say, this is going to leave us with this equation, okay. Or if you even want to further continue to divide, if you want to continue to divide, then it means that your stress in the steel rod, okay, the answer for your stress in the steel rod is going to be equal to what? The answer for your stress in your steel rod is going to be equal to, let's see, everybody, can we all divide this together? Can we all divide this together? Everyone, let's quickly pond this. That is 2 times 10 exponent 5. Okay, let's pond this together. 2 times 10 exponent 5 all over 1.2 times 10 exponent 5. Okay, and that is going to give us 1.66667. But if you like to, you can just still maintain it this way. Okay, so you, for safety reasons or accuracy reasons, let's just maintain it this way. Let's just maintain it this way. Or better still, if you still want to be dynamic, we can still convert. Okay, so don't worry, there is no harm in trying. So this can also give you something like this. That is, if you divide, you are going to get 1 point. Let's leave it in 4 decimal places. 1.666 what? 7. Okay. Then you bring your stress of what? Copper. And so that is what we don't know. So you realize that finally this is going to become our equation what? 5. Okay. This is now going to become our equation 5. So we can put equation 5 into equation 2 to get the stress of what? Copper. Okay. Now we know the formula to calculate for what? The stress in the steel rod. But I realize that we don't know what the stress in copper. Okay. So what we have to do is that we have to come and put equation 5 into equation 2. Then we can now use that to calculate for our stress in copper. This is equation 2. We are going to put equation 5 inside equation 2. Okay, so this is equation 2 over here. So we're going to put equation 5 inside this equation. Okay. So let's quickly do that together. Let's quickly do that together. And let's do that over here. So I'm going to write that as a subtopic. Don't get bothered. So we say that let's put equation 5 into equation 2. Okay. So this is it. Let's put equation 5 into equation 2. Okay. So let's put equation 5 into equation 2. As simple as that. As simple as ABC. So I want to quickly put down equation 2 even before I do whatever I want to do. For equation 5, you can see it. Okay. So let me just quickly rewrite equation 2 for you to see. And this is the equation 2 I'm talking about. This is equation 2 I'm talking about. For equation 2, we had 490. If you were writing along, you would have seen it. Once I move there, quickly take the screenshot. This is the equation 2 I'm talking about. Okay. So that was equation 2. This is equation 2 I'm talking about. Yes. So I'm going to write that somewhere now. Yes, as simple as ABC. So this is equation 2, and then equation 2 is equal to 490. 490.9375. Okay, exactly. Multiplying what? The stress in the steel rod plus 765.8625. Okay, yes, times the stress and the copper. Okay, yes, is equal to let's say 120 times 10 exponent 3. Yes, and this is the equation 2 we are talking about. So we are going to put equation 5 into equation 2. Okay, so this is equation 2. We are going to put this equation 5 into equation 2. So wherever you see the hot, the stress, and the steel, you're going to put that over there. Then you realize that it becomes uniform and you can use it to solve. We got equation 2 from equilibrium condition. We got the equation 2 from equilibrium condition. Exactly. So let's quickly do that quick, and then let's proceed. So this is it over here. We can now put our equation 5 into it. So that is giving us the 490.9375. Okay, then now over here I can put what 1.6667. Okay, so 1.6667. Okay, stress, multiplying the stress in the copper. Okay, plus let's say 765. Okay, 0.8625. Okay, exactly. Multiplying the stress in the copper, which is equal to 120 times 10 exponent 3. You see what we're having over here? So at the end of the day, we just have to simplify. Let's all multiply this together. Let's quickly multiply this together and see what we're going to get. If you multiply, let's say 490.9375, okay, times 1.6667, you're actually going to get 818.2455. Okay. So from that relation, this is what you are going to get. You are going to get 490. No, you are going to get 818. 818.2455. Okay. 2455. Let's say stress at C. Okay, or the stress in the copper tube plus whatever you are saying. Okay. So plus 76.8625. Okay. Multiplying the stress in the copper, which is equal to, let's say, 120 times 10 exponents what? 3. So you see now they're all uniform. It's a matter of making one the subject and using it to solve. Okay, we can add it. Okay, we can add it because you realize that the symbol over here and the symbol over here, they are the same. This symbol and this symbol, they are the same. So we can add them. You see the issue. So let's add these two now and we see how best we can proceed. So add it. Let's add 818.2455. Okay, plus let's say 765.8625. And at the end of the day, what are you going to get? You're going to get What are you going to get? You can quickly punch your answer in the comment section. You can quickly punch your answer in the comment section, as simple as ABC. So from here, we are going to get, let's say, we are going to get 151, 158, 1584, okay, 0.108, okay, which is equal to, okay, then you bring the stress, what, C, or the copper in the steel rod, or the stress in the copper tube, okay, which is equal to 120.